Hello everyone, I am Dr. Fawzulati giving some series of lecture for the course Discrete Mathematics. So in this lecture, we will discuss about the principle of mathematical induction. So this is a kind of a proof technique where the statement is of the form that Pn is true for all non-negative integers n or for all positive integers n or for some integers from some particular n onwards. Right. So this kind of statement I have. So I want to prove that we can use this mathematical induction technique. So we'll discuss that. What is that technique? So try to understand that in this way. So suppose I have an infinite ladder. This ladder is, I'm trying to draw a ladder. So this is a ladder and this is an infinite ladder, right? You can go up to like infinity if you can write this ladder. Now you have two kind of capability. One is you can able to go to the first step. You can able to reach to the first step, right? And you have one more capability, which is suppose somewhere you are in kth step, you should able to go to the k plus 1 step. So if you are in kth step, anyhow you reach to kth step. We don't know in which way, but if you are in k step, you should able to go to one more step, right? K to k plus 1. So if you have these two capability, you can reach the whole ladder. How? Because you said that you have one capability, which is that you can start the basic step, that means the first step. So you can go there, and then you have this one for any k. If you are in kth step, you should able to go to the k plus 1. Now you are in level 1, but you have this capability, right? For any k, if you are in kth step, you should able to go to one more step. So you are already in 1, so you can go to level 2 in the step 2 by this capability. Then you can go to 3 because you are in 2, so you can go to 3, then 3 to 4, 4 to 5, 5 to 6, like that you can write to the whole infinite ladder, right? So this is the concept of principle of mathematical induction. So I'll again discuss. So suppose you have a secret message and you have an infinite cube, right? You have an infinite cube of some human being. So they are in a cube. So they made the queue in such a way that like all of them are like that. Now you want to pass on a secret message. You want to pass on a secret message. So you should tell that if you should have two kind of condition, like if kth person know, k plus 1th person should also know, right? So if any of them, any of the position kth person know means next person will also know. This one is that, and then somebody has to tell to the first person the secret message. Then first person will tell to the second one, second will go to the third, third will go to the fourth. Like that, the whole message will be spread around the whole infinite cube, right? And you have one more example, like this kind of game all of us have seen, right? So you have a lot of bricks, you put them in such a way that you arrange them in such a way that anywhere if you push one of them, if the kth step brick, if you push that k plus 1, it will also fall, kth will fall, and then it will help to the, it will fail the second next one also, k plus 1 brick will also fall, and then somebody has to fail the first one, like then the first one will fall to the second one, second one will go to the third one, third one will fall down, like in this way all the bricks will fall down. Got it? So this is the concept of principle of induction. What you should have? You should have the basic step. That means somebody has to touch the first brick, or somebody should tell to the first person, or you should able to go to the reach to the first step. This is the basic step, and you should have an inductive step that kth step will imply that k plus 1th step. Kth person should know the k plus 1th person will also know, or the kth brick will fail to the k plus 1th brick, right? So these two if you have, then you can, all whole list of bricks will fall down, or you can write the whole infinite ladder, or the whole message will be like secret message will be passed to the all person in this infinite queue. So therefore this is the principle of mathematical induction. So to prove that A statement Pn is true for all positive integer n. A statement Pn is true for all positive integer n. Where Pn is a propositional function, we complete two steps. One is we verify that P1 is true, and that means the basic step, and we put that the inductive step, that we will show that the conditional statement Pk implies Pk plus 1. This is true for any positive integer k. If I have this two, that means the k person no means k plus 1th person will also know, or kth brick fall down means k plus 1th will also fall down, or the if you are can reach to the k step of the ladder, you can go to the k plus 1th. So these two you have, then you can say that the statement Pn is true for all positive integer n. Right? So here the basic step, it shows that P1 is true, but depending on your problem, you have to identify what will be your basic step. Sometime your basic step may be P0, depending on your problem only. Sometime your basic step may be 2, sometime your basic step may be 5. So your first step we have to identify, an inductive step is this one. Right? We'll do some example. Look at that problem. Show that if n is a positive integer, then 1 plus 2 plus 3 up to n is equal to n into n plus 1 by 2. So this formula we all know, that sum of first n positive integers, which is n into n plus 1 by 2. But how do we prove that? So we can prove this result using the principle of mathematical induction. So what we will do, we assume that this is the statement as Pn. Then you have to prove that Pn is true for all positive integer n. How do you prove that? So you have to prove that two step. One is basic step, another one is inductive step, right? So what will be a basic step? You have to prove that n is a positive integer. So positive integer start from where? Positive integer start from 1. So you have to prove that P1 is true. Now what is P1? That means in this case you should have only one term. In this case your n should be replaced by 1. And it is happening. If you n replaced by 1, that means 1 into 1 plus 1 by 2, which is 1, which is equal to 1. So the basic step is true. So what is the basic step? We have 1 is equal to 1 into 1 plus 1 by 2. Right? And therefore your basic step is true. That means P1 is true. So basic step is always easy. Now what is your next step? You have to prove the inductive step. Inductive step. Now how to prove the inductive step? Your inductive step is Pk imply Pk plus 1, right? So somehow if Pk is true, then it should prove that Pk plus 1 is also true. So how do you prove that? So assume that Pk is true. Assume that your Pk is true. What is k? For some k is greater or equal to 1. That means the integer, some positive integer k. Now Pk is true means what? So in place of n, if you replace by k, this is true. Therefore I should have 1 plus 2 plus 3 dot 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 up to k is equal to k into k plus 1 divided by 2. This is true. So this you keep it as equation number 1. This is our assumption that Pk is true. Now what is your job? You should prove that Pk implies Pk plus 1. Right? So basically we assume that okay, Pk is true. So we have to prove that with the help of this Pk, we have to prove that Pk plus 1 is also true. Right? Now what is Pk plus 1? In the same expression, we should have, in place of n, we should have k plus 1. So what is the left hand side of Pk plus 1? So therefore, we'll take the left hand side of Pk plus 1, which is 1 plus 2 plus 3 plus up to dot dot dot. It is k plus k plus 1, right? Because it will go up to k plus 1. It will go up to k plus 1. So this expression I have to prove it for, this is equal to the same thing you should have in place of k, you should have k plus 1. What is that? K plus 1 into k plus 1 plus 1 by 2. Now, how do you prove that? We have these things at some value from our assumption. What is this? So by equation 1, I have this value is equal to k into k plus 1 by 2. How I got it? This is by our assumption Pk. So the Pk will give you this value. And this one is remaining. What is this value? I am keeping it as it is. Now k plus 1 is a factor. So I am taking k plus 1 is common. So it is k by 2 plus 1, and this is equal to k plus 1 into k plus 2 divided by 2. But look at that, this is same as k plus 1 into k plus 1 by 2. So what it says, therefore you have pk plus 1 is true. So this is true. But when you have taken the help of pk, na? So that is there. So whenever pk is true, whenever your pk is true, what does it mean? It means therefore pk implies pk plus 1. pk imply pk plus 1. This is done, and your basic step also done already. P1 is true, pk imply pk plus 1. Therefore this whole statement Pn is true for all positive integers by principle of mathematical induction. Therefore by principle of mathematical induction, I am writing it shortly as PMI. By principle of mathematical induction, your Pn is true for all positive integer n. We are done here. So we have proved this theorem using principle of mathematical induction. So this is the formal proof of it. We have already discussed this one. So the formal proof, you can, if you want, you can look into this as well. Now look at another problem. Conjecture a formula for the sum of the first n positive odd integers. Conjecture a formula for the sum of the first n positive odd integers, and then prove your conjecture using mathematical induction. Correct. Now conjecture means what? Conjecture means, like we have discussed it in our proof technique chapter. To proof technique, the first unit, proof technique chapter. Conjecture is a statement which is proposed to be true, but which do not have any proof till now. If you have a proof, you call it as a theorem. If you do not have any proof, like if somebody disprove it, then the statement is invalid. So your job is first to conjecture a formula for the sum of first n positive integers. So by looking some partial evidence, you have to create a formula, and then you have to prove it using induction. So how to prove it? So first you assume that let Sn be the sum of first n positive odd integer. Sn be the sum of first n positive odd integer. Now, what is S1? S1 means what? S1 means sum of first one odd positive integer. What is that? It is 1 itself. You don't have to add anything because it's the single element. But what is S of 2? Sum of first two odd positive integer, which is 1 plus 3. But which is equal to what? It is 4. Right? Similarly, what is S of 3? S of 3 is the sum of first 3 odd positive integer. Right? So it is 1 plus 3 plus 5. But what is this value? It is 9. Now can you see some pattern? S of 1 is 1, S of 2 is 4, S of 3 is 9. Right? So 1 is basically, you can write it as 1 square. 4 is, you can write it as 2 square. 9 you can write it as 3 square. So S of 3 is equal to 3 square. S of 2 is equal to 2 square. 1 is 1 square. Can you see some pattern? Then what will be your Sn? So your conjecture is, your Sn must be n square. Right? Sn is equal to n square. This is your conjecture, but this how you have done by showing this partial evidence, right? But it is not proof. It is you are proposing that Sn is equal to n square. So this is your conjecture, Sn equal to n square. But what is your next job? Your next job is to prove this conjecture, right? So like how you have to prove that Sn is n square. Now what is Sn? Sn means, like, what is the expression? It is 1 plus 3 plus 5 plus, that means first n odd positive integer. Can you tell me what is the nth term? Like if your S2 is, the nth term is, the 2th term is 3. For S3, the third term is 5. So for Sn, what is the nth term? Yes, it should be 2n minus 1. You check that for all n, this is happening. S3 is equal to 2 into 3 minus 1. So 5. S2 is 2 into 2 minus 1. Right? Here it is only one term. So 2 into 1 minus 1. So for all cases it is happening. So this is your Sn, which is 1 plus 3 plus 5 plus dot dot up to 2n minus 1 is equal to n square. So this is now your conjecture. And we have to prove it using induction method. Now basic step is already done. Basic step. Your basic step is S1, but S1 is already proved, that we have already done. S1 is true. Now you should do the inductive step. Inductive step. So how to prove the inductive step? You have to prove that Pk imply Pk plus 1. Right? So assume Pk is true. Assume that Pk is true. Now what is your Pk? Instead of n, you should have k. So therefore 1 plus 3 plus 5 plus dot 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 up to 2k minus 1 is equal to k square. This is your equation 1. This is your assumption that Pk is true. What is your next job? Your next job is to prove that Pk plus 1 is true. Now how do you prove that Pk plus 1 is true? With the help of Pk you have to prove. Now what is Pk plus 1 is left hand side? So you can write it as now 1 plus 3 plus 5 plus dot 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 up to 2k minus 1. And what is the k plus 1th term? It is 2k plus 1. Right? So 2k minus 1 plus 2k plus 1. Why these are like that? Because each element's difference is 2. Right? So this is the kth term. Then 2 more difference. So 2k plus 1. K plus 1th term. So this is the left hand side of pk plus 1. But up to this much I have some value using pk, which is k square. So this is k square, and this was already there. So k square plus 2k plus 1. But this is same as k plus 1 whole square. So what you got? Therefore, we got the expression for pk plus 1. Therefore, I can say that pk plus 1 is true. But whenever your pk is true, you have taken the help of pk. Now, whenever your pk is true. Hence, by principle of mathematical induction, hence by PMI, principle of mathematical induction, your, in this case, like I have made it as S, na? So all these things I have taken it as K, P, but it will be S. S. I should write it as S, na? That's because mathematically, like your expression should be same. So by principle of mathematical induction, Sn is true for all positive integers n by principle of mathematical induction. And that means sum of first n or positive integer is n square. Or proof is done. I hope it is clear. So this is the proof of it. This is how we have identified we conjectured the theorem, by we have seen some pattern, then we made the conjecture. Okay, therefore that Sn should be equal to the sum of first odd positive integer should be equal to n square, and then we have proved by using the induction formula. Okay, we have one more example, that is the sum of geometric progress. Right, we have this one, and this one also we can prove it using principle of mathematical induction, because this we are talking about n is a non-negative integer. So how do you prove that? You can prove it like you assume that this is a Pn. Assume that this statement is Pn. that a plus ar square up to a r to the power n is equal to a r to the power n plus 1 minus a divided by r minus 1. So assume that this is Pn. Then how do you prove that? It is true using induction. So what is your basic step? Look at the problem. N is a non-negative integer. Non-negative integer starts from 0. So what is P0? Whether P0 is true or not, let us check. Now if this is Pn, what is P0 then? Only r to the power n, it will be a r to the power 0. That means the first term, right? So your basic step is, I am doing it little shortly. So your basic step will be that P of 0, but it is a is equal to a r to the power 0 plus 1 minus a divided by r minus 1, which is same as a, na? Because r you can take common, a you can take common, so r minus 1 divided by r minus 1. So therefore this is a only, and therefore P of 0 is true. Your basic step is done. Correct? Now what is your next step? Your next step is to prove the inductive step. Right? So inductive step, what we will do? Your basic step is done. Now we'll do the inductive step. Now the inductive step is pk imply pk plus 1. Right? So assume that your pk is true. Now what is pk? pk is a plus ar square plus dot 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 up to a r to the power n should be is equal to a r to the power k is equal to a r to the power k plus 1 minus a divided by r minus 1, where r not equal to 1, and this you name it as equation number 1. Okay, sorry. So your pk says a plus ar plus ar square plus dot 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 a r to the power k is equal to a r to the power k plus 1 minus a divided by r minus 1. So this is equation number 1. So you assume that pk is true. Now what is your next job? Your job is to prove pk plus 1 is also true. Now what is pk? pk plus 1, the same expression you should have, n is equal to k plus 1. This is true. So what is the pk plus 1 expressions left hand side? It is now a plus ar plus ar square plus dot 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 a r to the power k plus a r to the power k plus 1. But up to this I have some value using pk. What is this value? This is a r to the power k plus 1 minus a divided by r minus 1 plus a r power k plus 1 was there already, so a r power k plus 1. Right? Now I have to get this expression, this right hand side expression, as in the form of like pk plus 1. Now what we can do, you take that r minus 1 as a that numerator, so do the LCM and then just add them, a r to the power k plus 1 minus a, then r minus 1 into this, so what will happen? Plus a r to the power r minus 1, so I am producting with r, so a r to the power k plus 2 minus a r to the power k plus 1. But this and this will be cancelled out, and this is equal to a r to the power k plus 2 minus a divided by r minus 1. But this is the expression for pk plus 1. Huh? So what you got? You got pk plus 1 is 2. Therefore, pk plus 1 is 2. But how do you prove? You have taken the help of pk. Right? So therefore, pk imply pk plus 1. Therefore, pk imply pk plus 1. And you have already proved in the beginning that P0 is true. You have already proved in the beginning P0 is true. Right? And you said that pk imply pk plus 1. So basic step, inductive step, both the steps are done. Therefore, by principle of mathematical induction, Pn is true for all non-negative integer n. Proof is done. So the formal proof is here. Like you can say that P0 is true and then you prove that your assume that pk is true. From there you prove that pk plus 1 is true. So this summation expression you may avoid. You can do in this way, the way I have done, right? So to that I thought to discuss for this lecture. In the next lecture we'll discuss the similar kind of problem and a new method called strong induction. Thank you very much. Whatever your view, you may write in the comment box. If these videos are helpful, that also you can write. So we'll come up with a new video in the next lecture. Thank you. Bye bye.